To the first year student who has joined yesterday. Now today we are here for the IIST Colloquium, just for a briefing to the newcomers. This IIST Colloquium series is aimed to engage students and faculty members across diverse disciplines. And these talks are generally different from the regular seminar talk because the talks are designed for Colloquium to accessible across diverse discipline, and in general is very broad in nature, not specialized to any particular discipline. And we are happy that today we have one very distinguished speaker from IIT Kharagpur, Dr. Sandeep Saha, and the title of the talk is very interesting. So I request now Dr. Manu from Department of Aerospace Engineering to introduce the speaker.
Good afternoon, everyone. So, Sandeep Saha, so he is associate professor at IIT Kharagpur. So he is working in basically fluid dynamics and also interested in a lot of area, not just fluid dynamics. So today he will be giving a general topic. So how the dragonfly will fly without any visa or passport, right? Yeah, how it will migrate from Africa to India. So we were talking about this just one day before. I was new to this topic, so it was very fascinating for all of us. So I hope this will be a very enjoyable talk for everyone. So please join me to welcome Sandeep Saha to this IIST Colloquium. He worked in Imperial College, then he moved all over Europe, right? What I'm right, he traveled like a dragonfly. He may have traveled to France, he traveled to Germany, he traveled to then Cambridge, so then again back to India. So very much like not Africa to India, it's more from Europe to back to his native.
Okay, am I audible? Yes. So, good afternoon, everyone. Good afternoon. It's a very bright, sunny day, and I'm going to talk about the migration of dragonflies. You have seen dragonflies? Yes. Everybody has seen dragonflies. Have you seen this dragonfly? Some of you? Raise your hands. If you have seen this one, if you remember from your memory, this golden, bright golden, I mean there might be brighter ones you've seen, but I'm going to tell you a fascinating story about this one. Okay, so yeah, this one. Okay, so this dragonfly is migrating from India to Africa, and like Dr. Manu said, without visa or any passport required. But what is fascinating is, if you think of it as engineers, I mean, it is so small. I mean, you've seen dragonflies, right? They are only this much in size. If it is so small, how can it cross the ocean? Okay? Something so small can cross the Indian Ocean and come back. You can see here, I have shown. They are going from India to Africa and then they come back. So this is like a circuit. Okay? So I'll tell you a little bit more about this. So this is, I have to acknowledge the contributions of my co-workers, Kumar Sanatranjan and Ashok Power. They are my PhD students, and Professor Arnav is my collaborator on this project. Okay. And so I'll start with the introduction. So this is a sort of blown up view of this dragonfly. I took this picture in Kharagpur. You know where Kharagpur is? Some of you might know. West Bengal. This is the oldest IIT. Okay. The first IIT which came into existence, 1951. Okay. So I am from IIT Kharagpur, and this is where IIT Kharagpur is. Okay. And this dragonfly has sort of, it is found all over the world. Presumably, it is because it is, able to fly such long distances. Okay. It has got a wingspan of 8 centimeters. So this much or something, and the length is about 5 centimeters. So it's not very big. Okay, it is extremely light, 0.3 grams. I mean, you know what is 0.3 grams? It is nothing really. Okay, And with 0.3 grams, the challenge is that on other animals, like bigger animals like birds, you can put trackers. Now this device is got its own weight, right? Now if the weight of the tracker is such that the animal is no longer able to fly, or flying itself becomes so difficult that it cannot cross the ocean, then there is no point in putting such a tracker. Right? So we cannot study this using traditional methods of, how we study insect or how we study migration of animals in general. Okay. So I'm just trying to this entire fact sort of sink in that something extraordinary is happening and we are all connected to it. In India, this is happening. The world's longest migration is happening in India. So we should look at it with more sort of fervor, with more sort of passion and with more curiosity we should explore. There are many aspects which are unknown to us, and I hope you will ask me questions. Whether or not I have the answers to those, you can take it as your own sort of little reward from this presentation and pursue on your own. Okay? So the weight is this, and in this region, so these are all the biodiversity hotspots in this region. You know what are biodiversity hotspots? A lot of species, etc. are there. So they are incredibly important in maintaining the ecological balance. So for instance, certain species, the numbers are growing up, okay? So then they will eat up the other species, so that disturbs the balance. Now these guys, they are actually helping us maintain the balance, okay? Now if there are fewer in number, maybe the mosquitoes will grow. And if the mosquitoes numbers are very large, then you can have sort of malarial epidemics or things of that sort, okay? They are also probably eating some of the pests which affect our food security, for instance. Okay, so they are incredibly useful in many ways which we actually are unaware of. But from a biological and ecological perspective, there is an extremely important phenomenon which is happening in India. Okay, so and not just India but the entire region which it is connecting. So this is the route they kind of take when they are going to Africa, and this is the route when they are taking when they are coming back from Africa, okay, approximately. Now, if we go to the next slide, these yellow dots are where they have been reported by people, okay? And what is known primarily by the work of Anderson in 2009, although this migration has been sort of somewhat known from 1920s, so almost 100 years ago, okay, but this has not received much attention. It primarily came into limelight in 2009 when Anderson is a British marine biologist. He lives in Maldives and he found these dragonflies come year after year after year in the month of October, November. Okay? So typically they are found in Maldives in October, November, in Seychelles in November or a little bit later. These are just approximate timelines. Okay? And Mozambique in December. The next generation flies from Mozambique to Lake Victoria, and then finally they come back from Somalia to India in the month of May and June when it is raining in India. So you might ask, why they are migrating. But before I tell you why they are migrating, let us look at these numbers. This entire circuit is 14 to 18,000 kilometers. So this is presumably, extremely long distance which you can even imagine. And this is sort of thought to be the longest known insect migration. Okay? So the migration is happening at an altitude of 1,000 meters, and what I have shown here is the total precipitable water. Now the total precipitable water in the month of November, you see, blue means there is a lot of rainfall or there is a lot of moisture in the sky, in the atmosphere. So India is pretty dry, India is all black, whereas Africa is got a lot of rainfall. So if it is raining, then you can have rainwater accumulating in small pools. And in these small pools, the dragonfly can lay their eggs. Okay, and in these eggs, in these pools, you can have these larvae. They will hatch, and then the adult will come out of it, and then they will migrate again. Okay, so they can't lay eggs in any other thing but except for freshwater pools. Okay, so they need to chase the rains. So they are chasing the rain when it is raining in Africa. So in the month of November, we saw that, October, November, they were going from India to Africa. Okay? Now, in the month of June, India is getting a lot of rain, so they come to India. So this is the primary reason while the migration is happening. Okay, but even then, as an engineer, I think if you think of it, something so small to make such a large sort of migratory circuit is extremely extraordinary. Okay, so they have been known to cover some 3,000. So the way to Africa has 2 stopovers, Maldives and Seychelles, but the way back from Africa, they are crossing the Indian Ocean without any stopover. That is a distance of 3,000 kilometers in just a couple of days. Okay, so that is quite extraordinary. So we want to understand how they achieve this miraculous feat. Okay, and so in order to answer this question, I mean there are many aspects to it. Okay, and how do they find their way, etc. But we have focused on just 3 problems, which I will sort of discuss with you here. The first is, how long can they fly continuously? I mean, they have this limited energy reserves. I mean, they are like human beings, they have some limited energy reserves, some fat reserves or something, and they can constantly, they are not feeding, or perhaps even if they are feeding on the way, they just have limited energy reserves. Let's put it like that. Just like an aircraft which is flying, it has got limited fuel, so it is crossing the ocean with some limited fuel. So in that aspect, it is very similar. So how long can they fly with limited energy reserves? Now, if that time is enough to cross the Indian Ocean, perhaps not. So then they must be getting assistance from the wind. Okay. So then the next question becomes, well, how does wind assist them? Okay. Now, if wind is assisting them, then wind is not necessarily going exactly to Maldives or exactly to Seychelles or exactly from Seychelles to the coast of Africa. Then they have to, within the wind, they have to navigate their way. So how are they compensating for that drift? Because wind is taking them in this direction, they probably want to go in this direction. Right? So there is some wind drift associated with the migration. And how are they migrating within that sort of wind? Okay, so these are the 3 questions which we'll try and answer, and then I will, after telling you all this, I will take you towards, why we should be studying these kinds of problems, what can we learn from nature as engineers. Okay? So this is the outline of the talk. So I've sort of described what the problem is about. I'll quickly do a literature review. Then I'll talk about how we solve this problem. So the first part of solving this problem is that we try and estimate the energy reserves. It's just like, if an aircraft is flying, how much fuel it is carrying. Depending on how much fuel it is carrying, we can predict that this is the range of the aircraft, right? Okay, so we try and do that for this insect. We try and find out how long it can keep flying. Okay, the next part is, well, if it is flying for so many hours and it is going to receive some assistance from the wind, then what is the least time path from, say, for instance, India to Maldives or Maldives to Seychelles or so on and so forth. So if the least time path is sort of taking so much time, then if it flies for some amount of time, it is only possible to make this migration happen if you require less time to migrate than the least time path. If your migration is taking, say, 90 hours, which it takes, okay, so is it possible to cover the distance between India and Maldives in 90 hours or not? If not, then we can't have a successful trajectory. It is theoretically not possible to have this migration. Are you getting my point? Yeah?
Yes.
Okay. So this is the basic idea of how we go about solving this problem. Okay. So these are the 2 aspects, energetics and path planning. So path planning will tell us what is the least time path. Okay. Then we'll go on to see what precisely is the migration route they are taking, when they are migrating, and when they are migrating, well, what kind of angles they might be sort of compensating for the wind, and how does wind tunnel experiments sort of, what we can learn from wind tunnel experiments on these live dragonflies. We've conducted experiments of these kind on live dragonflies to learn what kind of angles or how they behave under crosswind, tailwind conditions. Okay. And then I will give you a few examples of other kinds of things where we have seen that biomimicry or bio-inspired engineering can help us improve the the system as such, okay, as an engineer. Okay, so this is kind of the outline of the talk. So when we started working on this problem, the major challenge was there is no literature. Mostly when you start working on any problem, you will find a lot of journal papers, you will go read those journal papers, and then you can form an opinion and you can start taking things from there. But here, there was no sort of available literature. What we had was bird migration theory, some wind drift compensation by migrating insects. So people have studied, as biologists have studied, how insects are migrating and how they are compensating for the drift. Okay, and there are also some observational studies, like I was mentioning, like you can have somebody who is observing the population of these dragonflies in certain islands and how that is changing with time. If the population rises and then falls, then there is a population influx and then there is a population which is leaving. Right? So these kinds of, so you don't really have the kind of first picture I showed, there's a globe and there's the migration route. So those kinds of things didn't exist. Okay, so we looked at these kinds of things. So bird migration theory has a drawback that birds are too fast, they don't rely on wind so much. These kinds of studies, the wind drift component, they are only at limited locations. Now, observational studies which are telling you about the population, they are not telling you which route they are taking. And finally, there is also isotope analysis. What isotope analysis is essentially, if you look at the eggs, they are hatching in water. The water has some deuterium, some heavy water content, and we can analyze that and you can estimate sort of the origins of where they have come from, because the heavy water content is going to reflect the lake or the freshwater pool where they have hatched. Okay, so that tells us that they are originating somewhere in the Himalayas, northeast of India, essentially. Okay, so that's isotope analysis. And the last sort of very simplistic sort of approach is that you assume that it's just blindly following the wind. Okay, it's just like when you put ink in water, it just flows with the water, right? Okay, so they assume that the dragonflies are just migrating with the wind, they're just going downwind, nothing else. Now, obviously, we know that if you go with the wind is not going to take you to your required destination. So that is also a problem with the. So we have problems from different. So it's a little bit like a jigsaw puzzle where all the pieces are there, but they're not all matching up. So we try to sort of come up with our own ideas. The first part was, if you have a small flying vehicle, then it has got limited flying time. As an engineer, that's what we think. Okay. And it has also got limited power to negotiate the wind, so it can't just go against the wind, and so you have to take advantage of the wind to get to your destination. So these ideas we brought in as engineers to try and solve a biology problem. Okay? Right. So first I talked about energetics and path bending. So let's talk about energetics. So here we have different kinds of powers which are required. So for instance, if you are flying, then you need to invest some power to just remain afloat. Okay, that is induced power. The next is, you have to overcome the drag. Like when the aircraft is flying, there is the fuselage, right? The fuselage will create some drag. So that is parasite power. The wings will create some drag, that is profile power. So when you add up all these powers, then what we get is the mechanical power which you need to keep flying. So for instance, if the dragonfly is flying say 100 kilometers at velocity 5 meters per second, then we can estimate how much power it is going to require mechanically. Okay. Now associated with that mechanical power, there is going to be some chemical power which is coming from the fat reserves.
Yes.
Right? Okay. So from there we can estimate the chemical power which is being required, and then we can sort of estimate how rapidly this energy is getting consumed. And at some point the fat reserves will go down to 0. So from these things we can run sort of a simple calculation, and then we can find how long it can fly. Are you able to follow?
Yes.
Okay. So we find that it flies for 90 hours, 1400 kilometers is the range, and it flies presumably at 4.5 meters per second. That is what maximizes its range. Okay, so we are giving it the maximum chance of survival. Okay, you travel the farthest distance at 4.5 meters per second. Okay, so how does this compare to the literature? Well, other people in the literature said around 120 hours, 96 hours. So we are not far off. We are not far off. And the advantage is that ours is a more conservative estimate. So if the dragonfly is able to reach the destination in 90 hours, it is more likely to reach in 96 and 120 hours. Okay, so ours is a more restrictive model. Okay, so if it is able to survive, then by other parameters also sort of more relaxed criteria, we will get the same answer. Okay. So in all of this, what we realized is that if it is flying for 90 hours and if it is reaching 1400 kilometers, certainly not sufficient to go across the Indian Ocean. Right? The Indian Ocean is much wider than 1400 kilometers. So it is going to need assistance from wind. Okay? So now we try and find out the least time path. Okay? If the least time path requires more than 90 hours, then obviously even theoretically it is not possible for the dragonfly to migrate. Given any other insect, I mean birds might be able to do because they can go faster, but this dragonfly cannot migrate. Okay? So how do we find the least time path? Well, essentially we assume that the dragonfly can move in a few directions, which are these 8 directions. We have wind velocity data from different organizations like NOAA, etc. So we have this. We know the dragonfly is going at 4.5 meters per second, which is the velocity which is going to maximize the range. We have assumed that it is going to go in certain directions, which is the resultant velocity direction. So now we can find out what is delta and what is the magnitude of Vt. Okay, once we have the magnitude of Vt, we can find out how long it will take to go from this point to this point, for instance. And now, if you have an entire cluster of points, then we can find out from this point to this point it takes so much time, this point to this point it takes so much time. And now we can have a search algorithm which tells us the least time path to go from source to the destination. Right? Yes. Okay? And with this, we can find the least time path between any 2 points. Okay, so this is all there in the algorithm. So let's move to the next thing. Now we also wanted to sort of look at how, if you just assume it's like a passive tracer, like the ink being dropped into water and flowing with the water, then how does it behave? Right? I mean, if you just go with the wind, which is much easier for the dragonfly, then it doesn't have to think and orient and decide. That is much easier, right? Then where does it end up? So we also did those calculations, and this is what we find. So this is the migration route. So, this is all happening at different time of the year. So, you see all these broken lines because the wind is also assisting in the migration. Okay. So it is going with the wind somewhere and somewhere it is going sort of when there is no wind, then it is rightly trying to head in the direction of the destination. Okay. So now if you see, this is the migration from Africa to India. This is somewhat around this time of the year. So around 15th of June, okay, a little bit earlier, there is strong wind from Somalia to India, and they are coming, Trivandrum is here, but they can reach here, they can also reach Trivandrum, okay. And the winds are very strong. So the yellow line is the passive tracer, so it's the ink kind of thing I was talking about, so you just go with the wind, okay. And the red is the actively seeking wind assistance, okay. So if you go with the wind, you can cover 2,800 kilometers in 45 hours.
Can I have a question? So you're assuming the wind direction and the drag to be unidirectional.
Yes.
But if it is other way, then how do you ensure that, because the wind may not be always in your favor?
At this time of the year, on this
So
day,
is it always true that this wind pattern is consistent?
I'm coming to that. Actually, there is no guarantee that, because the wind patterns are changing over, even few hours it will change. Right. So in order to compensate for that, this is an assumption. So we assume that the velocity field has been averaged over 24 hours. Of course, it is not true. It is changing. But to compensate for that, we've run our simulations for 6 years, 2002 to 2007. So 6 years we've run our calculations. So by assuming that over such long statistical periods, we would have gotten averages that, which reflect somewhere close to reality.
Because the average wind velocity and your drag is also related to the direction.
Of course, yes. We don't have we don't have that complexity in our model yet. Hopefully, in due course of time, we'll be able to. Okay. So this is when we are coming back from Africa. This is, whether you are passive or active, it doesn't really matter. But when you go to the next leg of the journey from India to Maldives, you see, if you go as a passive tracer, then you end up in the middle of the ocean and you're dead. Now, to think of an annual migration which is happening year after year after year after year, and you keep dying like this, I don't think it is making much sense, right? Okay. So if you are looking for your destination, then you kind of head where there is weak wind in a direction where it is possible for you to fly, and then you pick up stronger winds and then you end up at your location. And here you can see winds are playing a very strong, so there we have strong winds and you can cover long distances. Here you see it is taking 48, which is approximately the same time, right? But the distance has reduced significantly. So the wind is actually very important sort of factor in this migration. Okay, so somehow they are able to pick up the right kind of winds. How? We don't know. Okay, but the wind has to play a very important role. Now, in the next leg of the journey, it is even more clear. Now, you see, it is heading out into the ocean. This is Maldives. This is Seychelles. So you go along with the wind, and then if you keep going along, then again, this is at the end of 90 hours. Okay, you don't make it across. But if you are a little bit smarter, then you go with the wind to some direction, and then you change. And then when there is very weak wind, then you go towards your destination. At least this is what our least time algorithm is telling us. Okay, and this is taking 90 hours. So imagine if it can only fly for 90 hours, there is not much room for error. There is not much room for error. Okay, so it must be going somewhat along this direction, this kind of route. Okay, we will see if there is more evidence to what we are proposing. Okay. So, but one thing is for sure, passive tracer will never make it across. Okay? And biologically also, we can expect that dragonflies are smarter than just being passive tracers. Okay? So this is from Maldives to Seychelles to the coast of Africa, and here you can see there are strong winds here. So it heads south, picks up these strong winds, and then moves towards the coast of Africa. Whereas if you go just with the wind, then you can't make it. So it is actively looking for stronger winds. How? I don't know. Okay.
I have another question.
Yes.
You also mentioned that the height is about
1,500 meters.
So the wind pattern is also slightly different.
This is at 1,500 meters. Yes.
So it appears to me also that they know how to float.
Yes. They are probably looking for thermals and trying to soar with.
So in your energy equation, how much energy they will require to change the.
We have not. Yes, we have not. Sort of accounted for the fact that the height variation is going to affect, but we have assumed that it is more or less going at a constant height, which is the height which is known. But within that, they can go up and down by 10, 15, 20 inches, which can significantly affect the energetics. So if they glide and lose 10 meters, they would have probably covered a huge distance, right? So those kinds of things are already there, but we don't have that complexity. I mean, for us, the fact that it is somewhat possible was the fascinating. So we are trying to reach a point where we can show that it is, from an engineering, you've done some calculations, some easy calculations, and it seems like it is actually feasible. That's what we are thinking. Yes?
Sir, if I'm not wrong, you said that the time they migrate into India is about June, right?
Yeah.
So if I'm not wrong, and that would be with the southeast monsoon winds.
Yeah, they're coming with the winds, yes.
So during that time, the humidity and the cloud density in the Asian part, South Asian part is very high and dense. So doesn't that affect how the energy consumption and how they move? Also, you said
that's a good question. Really good question.
Also, you said the altitude is about 1,500 meters, right? And the main cloud density is at approximately about 2,000 meters. I looked at
Sure.
So it's approximately at about 2,000 meters. So doesn't that also
affect the visibility?
No, not exactly visibility, because if I'm not wrong, insects do not have that strong vision sense. So doesn't that affect the sense of direction?
So, both are very good questions. I don't have answers to them. What I can tell you from my little understanding of biology is that they have magnetic compass and sun compass. So with the presence of cloud, I don't think that should be affected. Maybe if they are picking up the sun and they are lost in the cloud, I don't know. But maybe the magnetic compass still works.
And that question about humidity,
I think they are actually looking for gradients of moisture. Like when I was showing the first slide, this one. So you see, I mean, it is obvious that there is a strong moisture gradient. And I think that is what is governing their sort of direction, general direction. Because I forgot to mention, sorry, that this takes 4 generations. It's not the same insect which goes across time. Okay, so the insect which starts off from India, it reaches Maldives, perhaps Seychelles, and then the next generation is probably flying to Africa, and then another generation. So I think here in this slide, yeah, it takes 4 generations. So one generation from India to Maldives or Seychelles, or even more. Then the next generation here, Mozambique to say Lake Victoria, and then finally the last generation. So the 4th generation comes by. So the grandchildren's children. So now every generation is moving in a new direction. So probably they are picking up moisture gradients, and that is what is assisting them in the overall search for their, where it is raining. But this is just a hypothesis. I don't have evidence to concrete sort of give answers to concrete answers to what you're asking. But both are excellent questions. Okay? Yeah.
Always flies only in the northern hemisphere.
No, it is crossing.
It's going south.
It crosses. I mean, here you see, it is crossing the equator. It is crossing the equator, and then
because once it crosses equator, you have southeast trade winds.
Yeah.
That's mostly easterlies.
Yeah.
Trade winds in southern hemisphere will be southeasterly.
Yeah.
Essentially. So
And then when it is coming back, it is taking the
that is
yeah.
that is the southwest one.
Yeah. So it crosses the equator in Africa. Once it is crossing over the ocean.
No, June is fine because that's the southwest direction. But I was thinking the winds that you are showing just
Here?
south of equator is mostly easterlies, but they essentially would be southeast winds.
In the month of December.
Yes.
Maybe it is changing direction.
Not on the sea, not on the sea. I think what you are referring is on the land.
This is generally not the ideal circulation. So over the sea and land. Anyway, it's fine.
Yeah.
Essentially easterlies.
Well,
It's more southerly compared.
yeah.
Sir,
Yes.
so one question, sir. These simulations, were they assuming that it was a perfectly dry weather?
The weather is just, we are just looking at the wind direction and the wind velocity.
But
We are-
actually, I mean, at that size, water and surface tension takes a place. I mean, water is heavy for 0.3 grams. I mean, if it sticks.
Oh, you mean if it is raining and it is flying in a rainy condition?
Like you pointed out, like.
Very good question again.
I mean, that will affect the.
If you have seen, I observe them when they are flying, and rain seems to not affect their movement at all. I mean, how they are flying in rain, I don't know, but they don't seem to be affected even in rainy weather. When I'm like seeing them, they just keep hovering and then they go and then they return and the rain. Even, I don't know. I mean, the droplets might be big, and even then they are able to fly without much trouble and. Yeah, I mean, excellent question. I don't have answer.
Actually, the earliest rain is
Yeah.
high moisture. So that is basically what's called the intertropical convergence zone.
Right.
It's the convergence of both the northeast and the southeast.
Yes.
So you have a lot of clouds
In that region, yes.
possibility of rain.
Yes. But I think they still are looking for moisture gradients. That is what I think. Otherwise, one generation is moving south, the next generation is moving west, the next generation.
It's the next generation, right? That's second.
I don't know. Okay. So, so now I'm trying to convince you that what I'm doing is making sense. Okay. And you're most welcome to even, oppose. This is my sort of, argument in favor of what I'm hypothesizing. So, for the migration to happen, you need two things. One is precipitation at the destination, and the other is the wind assistance. Without both, there is no point in having the migration. Okay, so the green here is the migration, is the precipitation at the destination. Okay, the green is indicating what is the precipitation at the destination. The blue is showing the number of days we have had successful trajectories over a period of 6 years. So, for instance, if you look at the month of June, you can see there are approximately 90 days over a period of 6 years. So, you can say on average 15 days in June you are having favorable winds. On average. Are you following? Okay. So, if you are coming from Somalia to India, then May, June, July is a nice time to come. Can you see? Because you are having precipitation and you are having a lot of wind assistance. If you come later, then you can come, but then your next generation will hatch when there is no wind to move away from India. Are you following?
Yes.
Okay, so May, June, July is the right time to come to India. And that is what has been observed in the sort of, what people have reported, sightings. So, if you are going from India to Maldives, you see September onwards, October, November, the retreating monsoon is the right time to leave India. Okay, so late in the year. If you are going from Maldives to Seychelles, then late in November, December and early part of the year is the right time to go. And from there on to the coast of Africa, early part, February, March, April is the right time to go. Okay? Now if you go, this is what our model is predicting. Okay? And these are all the papers which have been sort of on this topic. In fact, we have papers from 1924, 1913. Okay? So over a period of 100 years, so many papers have come out, which have said something about, these being cited, etc. These dragonflies. So what people have said is that in the month of October to December, in the month of November, they have been found, and our model is predicting the same thing. In Seychelles, November, December, March, November to April, we are saying in the month of January to March. I mean, you can see it's the curve is going up and down, right? I mean, the probability of migration. Same thing in Africa, all these papers, they are saying that December, February, November, December to January, March to April, December to March. So even with a very ad hoc crude model, we were able to get the approximate migration window. And that gives us confidence in what we are doing. Okay, so this is what's convincing, because 100 years of papers, and they were all sort of independent inquiries. And there is one theoretical sort of approach which is sort of getting there. Okay. Even this last one, I mean, in 1924. So Fraser did not say that these guys are migrating. He just said that they have been seen to leave the west coast of India, Western Ghats, and go over the ocean. Which is very surprising. Why would they go over the ocean? There is nothing to do over the ocean. So they were seen to leave India. Okay, now I'll show you a movie where you can see the actual migration of dragonflies. So this is a swarm which we saw in Cherrapunji. You know Cherrapunji? Cherrapunji is in Meghalaya. Okay. So I'll play this movie. This is what the swarm looks like. So this is Cherrapunji. So you can see. Okay? So the actual picture is a little bit more complicated. I mean, when I was showing in the beginning, there was only one line connecting different places. But what actually might be happening is like a branch network. So part of the population goes along the yellow line, part of it goes along the red line, part of it goes along the blue line. I mean, these are all feasible. And they meet up in Maldives again, but maybe one population reaches earlier, one population reaches later. So actually it's a lot more complicated. The reality could be a lot more complicated. Okay, and each depending on which route they take and when they find favorable conditions. And some of it might even perish on the way. Okay. So now so we've talked about, the energetics, we've talked about the wind resistance. Now I come to wind tunnel experiments where we try to see, if you put them in the wind tunnel, what is the wind tunnel? Some of you might know. It's just a large sort of device where we can control the flow, simply speaking. Okay? And we can mount the dragonfly and we can sort of change the direction in which the dragonfly is facing and see how the wind is impacting its flapping behavior. Okay. So this is our wind tunnel, this is the dragonfly, and we can measure forces. And now you can see, so there is headwind means the wind is coming from this direction, tailwind means it is coming from the back. And within that, we can change the direction in which the dragonfly is facing. So that is like simulating crosswind, which is true for most of the trajectories we see. There is a lot of crosswind. Okay. So this is our high-speed camera. This is our force sensor output. This is what the setup looks like. What you see here is the wind tunnel. That greenish blue thing is the wind tunnel. Okay. So we can control the flow very well. And inside is the dragonfly. So usually the dragonfly is not constantly flapping. It is flapping for a while and then it gets tired and then it stops flapping. And then it just modulates its wings in like this way to generate some forces. Okay. So when it is flapping, we call it the burst, and when it is not flapping, we call it passive. It is just passive line. It is alive, but it is just passive. Okay. So what we see here for different angles. So at 180 degrees, there is just pure tailwind. Okay. So there is no need to generate any side force, because side force is what is compensating for the drift. Okay. So at 180 degrees, there is no need. So the forces, the side force which is being generated is very small compared to its body weight. Now at 175 degrees, we get two data sets. So the star is passive light, the burst is the sun. Okay. So now if you think that the dragonfly is getting moved in this direction, then it will want to compensate. Okay. So it will generate some positive side force. So by the burst mode, it is generating some positive side force. So passive, it is generating some force. If you take that as the sort of datum, then the burst, it is always trying to generate some positive side force. So it is trying to compensate. Okay. And that thing is same observed for other angles also. 175, 170, 165. So this is primarily in tailwind and then some crosswind. Okay. So from this we get to know that the dragonfly is constantly trying to compensate. Okay. Now there is more data, I'll skip all this and I'll show you how the dragonfly flaps in headwind and in tailwind, because that is a large difference. Okay. So this is what the dragonfly looks like when it is flapping, and please pay careful attention to the movement of the wings. So in this headwind you will see large amplitude flapping, but in tailwind you will see very small amplitude flapping. Okay, I'll just play. Did you see? So the amplitude was very large. Now tailwind, the amplitude is going to be very small. Please pay attention. Okay? So, did you see that? Okay, so there is significant. So the dragonfly is able to understand that the wind, this is a headwind, this is tailwind, and this got a measure of these things and is modifying its kinematics in that way. Okay. So now I'll play this movie, but because we have less time, I will skip a lot of it. So need not worry about the technique, but I will show you what the flow field around the dragonfly looks like. This one looks like. So, but I think I just wanted to get the sort of a feel of what it looks like. The flow field is so complex. There are so many vortices. There is wing and the vortex interaction. So many things are happening. Now it has got a pair of wings, so it can do out of phase and it can also do in phase. So it has a lot of control. So I mean, traditionally when we design aircraft, we are thinking of the aircraft wing. Then there is the elevator, the tail, and all those things. This is a completely different way of flying. Fascinating, isn't it? So we also started looking at other long-range migrations. This is migration of butterflies across the Atlantic Ocean. Okay. So these butterflies, they are known to migrate from Africa to the northeast coast of South America, which is French Guiana. So these kinds of migrations are happening, and we should be studying them. They have huge impact. I mean, butterflies are pollinators, so they affect the pollination process, and that is extremely fundamental biological process. Okay. So this is the route for the butterflies. And these are the organs with which they are able to sense the direction of wind. I'll not go into the details, but this is at 10 micron level. So if you have a scanning electron microscope, which is a very advanced device, you can cut open the dragonfly wings, and then you can look deeper into what structures they have at the micrometer scale. And from there, we are learning that they possibly are detecting wind. So you can think of an engineer who is devising sensors which are working at micron level. So it's a very compact device which is doing many things at once. Okay. That wing might look simple. All those who played with dragonflies in their childhood, that wing is actually a piece of engineering, marvel of engineering. So I'll give you some very basic. So the whole point was, I mean, until now I was trying to solve a biology problem using engineering techniques. The reverse is also true. As an engineer, we can learn from biology, like I was showing you this example of how it is detecting wind. Okay, we can learn from biology. Okay, I'll give you a few examples. This is a gliding bald eagle, and this is an Airbus A350. And can you tell me what is the similarity between the two? The wings. Okay, so what nature is doing, inherently, we are learning from nature. Not that Airbus was looking at gliding bald eagles, but there is similarity. So this is an example of biomimicry. So we are copying the nature's functionality directly and implementing in some engineering device. Okay. This is another example. Owls are very silent flyers. Owls, they don't make much noise. Okay. So people have looked at the trailing edge. This is the trailing edge. This is the leading edge. This is the trailing edge of the barn owl wing, and they have implemented it in these kinds of fans. Can you see these kinds of serrated, which is going to reduce the noise the fan is making. Okay. And this is the maple seed. Some people have seen maple seed. In India also we have these kinds of seeds. Okay. So they start to auto rotate, and they are making these kinds of fans. So you can think of being engineers who are making new kinds of devices which probably is very efficient in terms of the power consumption or things like that. I mean, even that dragonfly is a very efficient flyer which is consuming very little energy to go across the Indian Ocean. So it's a source of inspiration for us. And who can tell me about these two? Someone who can tell me about these two? Huh?
Sound barrier is very difficult.
Not quite sound barrier. This is not going at Mach 1. But yes.
Those design lessons the tunnel.
Yes. So the person who was designing Shinkansen was an avid bird watcher, and he observed that kingfishers are more successful hunters than others. So it is because of their beak design. Now, when you are entering water, you are going to create pressure waves, and those pressure waves, they reach the fish very quickly, and the fish knows that something is coming, and they run away. Now, if you reduce the magnitude of this pressure wave by the way you are entering, then obviously the fish will not know, and then you can become more successful. Of course, this is by evolution, all this has happened. Kingfisher is more successful hunter, but this is what this picture is telling you about Shinkansen design. So what happened in Japan, every time, when you are entering a tunnel at very high speed, you start compressing the air. The train is going at very high speed. It is like a piston, almost like a piston. You can imagine you are compressing the gas in front of you, and then when you are coming out, all of this is released, and then you hear a large boom which is affecting the ears of the people who are living in that region. Now, with that same example, he thought of sort of solving this problem by making the nose more like the beak of the kingfisher. So these were some sort of very obvious examples. Now I'll try to share some examples which are sort of less obvious from my own research. Okay, and I'll try to wrap up very quickly. So this is the dragonfly wing, and this is a delta wing. So those who've seen fighter aircrafts, they have these kind of delta wings, right? The delta wing is a very nice way of flying, but you can see this region where the green thing is telling you it is where lift is being generated. In this region, there is not much lift being generated. So we put some of these corrugations which the dragonfly has in that region, and that tells us that actually it can help improve the performance of these kinds of wings. So I'll not go into deep, but this is the lift. So the lift compared to the baseline case, which is the black line, which is the normal delta without the corrugations, the lift goes up. The drag also goes up because now we've generated a few new vortices. Okay, so that increases but the overall lift to drag ratio is improving. And this is the range where you are gliding. Okay, so we've implemented something we learned from the dragonflies and with zero cost. We reduced the drag, we improved the lift to drag ratio, and there was no cost. We just removed a bit of the material by introducing the corrugations. Okay. This is a wind turbine which sort of we thought of making. Now, when we looked at the flow field, we saw that there is one wing which is going after the other wing. So there is some sort of wake recapture. Wake recapture means that the wake is the flow behind the first wing, and we are trying to capture some energy from that. Okay. Now you can implement the same kind of idea in a wind turbine, and that offers certain advantages because, for instance, if it is more efficient, then with the same device we can generate more power, or it can work over a larger range of conditions. So it can work for a larger part of the year. These kinds of advantages can exist. Okay. So we did this. So we put in two rotors, just sort of motivated by the dragonfly in this way. And we did some analysis, and it turns out that indeed this design is better. Now, I'll leave you with the last example. So this was, have you played darts? Some of you might have played darts.
Yes.
Okay. Now, have you seen the wings of the dart? They play an incredibly important role in the aerodynamics, in ensuring that the dart is able to penetrate. Here we see these are 4 different experiments, and in all 4 of them the wings are there, and the dartboard is being pierced by the dart. In all 4. Now in the bottom 4, we have removed, can you see? We have removed the wings, and it is just simply, it's got a tumbling motion and it is hitting the dartboard and it is not able to pierce. That is because it is not able to maintain that sort of angle when it is approaching. The pointed part is not approaching and it is not hitting the dartboard. Okay, so the wings are a very important part of the aerodynamics, and they control the motion. Okay, so the aerodynamics is very important. Now, if you see this movie, you will see here that first it is pitching down, then it is pitching up, and then again it is pitching down. So if you think of this dart, it's got a heavy front which sort of wants to go down, and then once it is down, the wings, they are generating a motion in this way that is correcting it, and now it is at a positive angle of attack, and then it is giving a moment in this direction. So it's got a self-correcting nature. That is what is allowing it to pierce the dart. So that is the physics in short. So this is what the flow field looks like. I'll skip all this. So the dragonfly is something which can fly, and the dart which can stabilize itself. So we thought of combining these 2 ideas. So we thought of combining these 2 ideas in this kind of a new micro-aerial vehicle we conceived. Okay, it looks very different from the ones which you see, but it might work. We haven't made it fly yet. Okay, we're just inspired by the dragon. Okay, so I think this is where I'd like to sort of summarize. And so we looked at the migration of these dragonflies. We looked at a few examples of how we can learn from nature, and we also looked at how we can take inspiration from nature and apply those concepts to other topics, and that is sort of closer to bio-inspired. So biomimicry is we mimic nature, and bio-inspired is we take inspiration from nature and apply it to some other device. So I think with that I will end. And this is a swan which is flying in ground effect. Do you know what is ground effect? Yes, economic. So this swan automatically knows about the ground effect, you see. It knows about the ground effect. So nature has already discovered a lot of these phenomena which we try and exploit, and there is much to learn from nature. I mean, all those questions which have been asked, I'm sure if we pursue those questions, then we'll get to learn a lot more which we can take to engineering. Okay, so with that I think I will end my talk. Thank you. So this is my email address in case if you want more questions, then you can write to me. Okay? Yeah, questions.
Yes, sir. Actually, I just want to related to the fluid flow. So I've heard that vortices carry like high energy bends, so it helps in creating lift, but outside the same thing creates cracks. So how does the vortices on the there are these little bumps that help create vortices. So how does that help?
I don't know. You're in first year?
Yes, sir. I'm out of it.
I'm struggling to explain. Let's say that the presence of these corrugations, they are helping the flow remain attached to the surface. Like at these retroflow, the behavior of air is slightly different from what you see on aircraft, etc. So typically what happens is that this is the wing, and if you increase the angle of attack, then the flow will separate. It's called stall. Okay, and let's say at these Reynolds numbers, certain phenomena happen, and with the help of these corrugations, you can keep the flow attached a little bit longer. Okay, because you have these vortices, and those vortices they can sort of they can be used to generate more vortices, which keeps the it's not exactly like vortex generators, but somewhat like that.
Yes, that was my exact question. Like how do the vortices help exactly?
Oh, you're injecting momentum into the boundary. No, I did not want to talk about that. I mean, let's say in 1 or 2 years' time, I can be more comfortable in answering your question.
As regarding the red line and yellow line, there is a relative motion between wind and the dragonfly. And also there is humidity. Why you don't consider the air friction and some friction due to humidity in your energy conservation and mechanical
air friction is there in our model when we consider the energetics.
So but in that calculation of mechanical power,
we can have a more sophisticated model where we are looking at the motion of a sort of, let's say a particle which is governed by, but that is a more complicated problem. We haven't managed to reach that point where we can solve that problem yet. But it is foreseeable, in the foreseeable future we should be able to do that.
thank you.
Yes.
Sir, good afternoon. As you said that this phenomena was known for over a century, the transmigration of dragonflies. How did you come to know about it?
TED Talk.
TED Talk?
TED Talk. There is a TED Talk by Charles Anderson. He is the one who popularized this, migration. He has got a TED Talk. I mean, if you just look up Charles Anderson and dragonfly, you will find this TED Talk.
Oh, thank you. So, sir, also like if we also want to be inspired by nature, so what steps should we take?
Just observe everything around you. Just simply observing. I mean, I got a question that, how do they fly in rain? I mean, I have just observed that how they fly in rain is particularly not very different from how they fly when there is no rain. So just keep observing. I'm sure when you observe, then something will click and then you can Google and maybe there is information, maybe there isn't. So that's, but be more observant, be more curious.
Thank you, sir.
Good afternoon, sir. Sir, as the dragonflies are flying in the part of equator at the time where it is summer, isn't it possible that warm air currents help them fly?
Yes, it is certainly possible. We have not accounted for that in our model, but it is very much possible that they are, taking those thermals and gaining altitude and then gliding for some distance and then flapping. So that sort of complexity is not there in our model. But it will only make it more feasible. So the answer is going to remain the same, although our inaccurate answer is telling us the same thing.
Good afternoon, sir.
Yeah.
Sir, as you have said that they travel from in the month of May and June and October to November. But these are also the time of tropical cyclones in India. So,
yes.
Do these cyclones affect?
That is a very good question. Actually, very good question. So, what I think is that they can detect these kinds of things. They can detect wind conditions and low pressure, etc. Because they are flying at very high altitude, so they probably even detect changes in pressure and those kinds of things. Now, generally the cyclones are also moving in a certain direction in each. So whether they take advantage of those cyclones and move in favorable directions is possible. I mean, if you look at the one from India to Maldives, they probably are looking for that sort of so this, what did I put? Presumably this is like a cyclone kind of thing.
Yes.
So they are able to detect and they are able to take advantage. Probably, but I cannot claim for sure, but it might be happening. It's a very good question.
Thank you, sir.
So you were saying that it will detect, right? Like,
Detect?
It will detect that.
Yeah, velocity gradients. I mean, over large regions. Yes.
I think that it is a probability that if 100 flies are going, the 100 flies, 2 only will win the race. Like.
Oh, you mean that a lot of them will perish and they will die? Yes, but I
It's
mean,
not
that,
that
so
predict.
this is the next question which I am trying to answer, that if say, X number of dragonflies are migrating out, then what percentage reaches? Because the ones which die, they are going to get consumed by the marine life.
So you just found that this is the only way that, what I can say, this is the path. If the dragonfly follows, it will success.
Yes.
You just found that one.
Yes. I mean, if it is possible.
It's not that like all flies will follow that path. Because it's just a probability.
This is the way I think about it. I mean, of course you can challenge me. So you have a swarm. Okay, and the swarm is migrating from India. So if one of them is able to, it is theoretically possible for one person in that swarm, the entire swarm is going to go along with it.
Yeah. So it can be a group like one.
Yeah. So, but if one is going,
like,
no, I mean there might be a leader or something of that sort, and that leader is being followed by the rest.
Yeah.
So if the leader is able to find, then the rest will also reach.
Then what you are trying to find? I think it's just a probability.
I didn't quite get your question. I mean, what I'm trying to show is that there is a theoretical possibility of this migration happening, and that theoretical possibility is leading us to the migration window which is matching. So it seems like that is actually what is close to what is happening in reality.
So you can understand my question. I think, like I'm saying that if 100 flies are going, 2 will success. Okay. Like not everything will follow this path, right? right?
But the entire storm will move in one direction. You saw that in the movie that the entire storm was moving in.
It's not like a swan can be different, sir. I'm saying like it's a dragonfly.
No, that swan was the migrating dragonfly. Swan. They were all moving in one direction. I mean, do you remember this movie? They're all moving in the same direction. They're all moving in the same direction. Okay? Yeah. You are not okay.
Sir, good morning. Good afternoon, sir.
Yeah.
Sir, my question is that you said that dragonflies are attracted to more densely monsoon type climate.
Yes.
So, in that case, instead of remaining in like a constant circuit from India to Africa, can't they just go to a place that remains in a dense monsoon climate all year round for like Philippines or Indonesia, that kind of?
They might be going, we have not that has not been reported. I mean, if you look at this yellow dot map, I mean, it is very much possible that they go over the direction and remain there as non-migrants. They might settle down. It is possible.
Okay, so this is going to be the last question because we have to start the
Just one or two more questions we can take.
Good afternoon, sir.
Yeah.
My question is, why we are just studying dragonfly, not mosquito or housefly?
Why we are?
Just studying dragonfly, not mosquito or housefly.
I think a lot more people are studying mosquitoes and houseflies. I am the only one who is rare and studying dragonflies.
But sir, and China has created the mosquito-sized drones. Why are we not discussing about mosquito or housefly?
We should definitely. I mean, there is no reason to, but it is just that I started working with dragonflies. Houseflies and mosquitoes, they have been studied by other people, definitely. I mean, there is literature. I mean, I didn't discuss it, but definitely there is literature on that. People are working.
So now the question is a bit of confusion. So that originally we had the points where they were reported as the original data.
Sorry, one second.
Sir, at the start we had the points where the dragonflies were spotted at the original start of data. So later on you
mean these points?
Yes, they were. So later on you used that wind velocity and the dragonfly velocity to track the path in between of those points. Please just can you sir tell that how did you got those dragonfly velocity part? That I don't know.
This one?
Yes, sir. How did you figure out the direction of the dragonfly velocity?
No, this is an assumption that they are migrating only in 8 directions. That is just a simplification. We can choose 16 directions also.
No, sir. I wanted to ask the path that we got between 2 points, between any 2 destinations, the path there that was. Yes, the path that was between 2 locations was resultant of wind and the dragonfly.
Yeah, so this is the least time path between location 2 and location 3. So if you draw a grid and try to, now we have the time because we know the VT. So we discretize this into smaller, I have not shown the grid points, but this is broken into some n by m matrix. Okay, and then we are trying to find the least time path between these two. This is the least time path for this given velocity field. Are you following what I'm saying?
Sir, you took that the dragonfly velocity is taking the least time path.
Yeah, that is the assumption, yes. I mean, if you think from a biological point of view, you will want to minimize the time it takes between the migration so that you arrive with the least amount of energy spent or something like that, and then you can capture and there is least risk, so to speak. So biologically speaking, seeking the least time path is the best thing to do. Of course, there can be differences. For instance, the male and the female, they have different objectives. So the males will try to arrive early and they will try to capture. The females will arrive a little bit later and they will choose the best place to lay their eggs So there are differences, but to begin with, the first sort of approximation is that they take the least time path.
Sir, I'm just a little bit of confusion. Sir, isn't that yellow one the least time path? But
No, the yellow is the passive. If you just go with the wind.
Sir, the yellow line became red line because the dragonfly velocity compensation.
It's for the least time path. You have to understand what is least time path in a n by m matrix.
So basically what this is, if you want to go from here with the assistance of wind, then this path is the least it is going to take. And the yellow is if you just keep floating with the wind.
With minimum energy.
Okay, so I think we have to stop now. So thank you very much, Dr. Sandeep Saha, for wonderful talk. Saha is available in the aerospace department till I guess somewhere 5:30 or 6 o'clock. So if anyone of you wants to interact, you are welcome. So we close the session here, this session, and the next session will start, I guess, part of the another session. Thank you very much.